Electric fields, chapter 19 for physics. Well, first of all, an electric field is just the area around a charge. So if I have a charge here, it's just the area literally all around it. Now, Michael Faraday noticed, and he did all sorts of experiments with it. You'll later in a few minutes when we talk about capacitance, which I know you don't know what that is yet, but it's named after him, just to give you a heads up. But he did all sorts of things to see how a charge works, and he noticed that there were these lines of force that would come out from the charge. There was an infinite number of them. They were vectors. Just to show you in your book, there's a pretty one right there that he has. And like I said, he just did lots of experiments with them. Now, there's actually 4 characteristics of lines of force. In no particular order. They always come from a positive. Another thing as far as that has to do with them is the number of lines of force. I'll see L of F. The higher, the stronger it is. Also, the closeness of the air or the lines of force is how strong it is. So if they're really close, they're really strong. And the last one is they never cross. Now, this is on page 431. It's in a little kind of manila brown if you want the fancy, but there they are in official physicsy language. But the lines, of course, never cross. And so he did some experiments with them. He did things with test charge. Now, a test charge, you can see on this one, it's a super small, it's negligible, it's just enough of a charge so he could see what was going on in certain areas. For instance, this is also in the book. I've always loved this picture. But here, there's several things happening. In this one, notice how there's the one charge and all the lines coming from it. Well, you know that one's positive. Well, look at this one. You've got 2 charges, and notice how they seem to be connecting. So that means one of these are positive and the other is negative because charges always go from a positive. Notice how this one, they're trying to go together and then they're repelling, so guess which one they are? You got it, 2 positive. This one, those 2 are repelling, so you know those are positive, but see how those are attracting and those are attracting? So positive, positive, negative. Now, you can find all sorts of things with electric strength. You can find it literally by experiments. You can also do it with vector addition. Just different ways to work with it. Now, I know that you've heard me the last few minutes say this word, I believe. But electric field strength is just how strong the charge is as far as in that particular area. The formula for it, we use E for electric field strength, and the math we'll get to next week. But electric field strength, force over charge. And what you have is force, of course, measured in newtons, charge measured in coulombs. I'll write it out there for you. So that is the unit for electric field strength. Now, there's also another formula. And don't worry, on the test, I am going to give you the formulas. The formulas themselves. I don't tell you the units and stuff, but literally the formulas themselves. This is also another way that you can find electric field strength. The constant K is 8.99 times 10 to the ninth, and technically the units, Newton times meter squared over Coulomb squared. But as far as that's what K represents, Q, of course, charge, and R, of course, distance. So the way you know which formula to use has to do with what they give you. So even though the formulas, there's several of them, they're not that hard to deal with. Now, something you might not realize about electric field strength, notice how, look at this formula just for a second, for those that like to see how things work. If you were to cross multiply, you would get force equals EQ, which is super similar to force equals MA. So the electric field strength has a lot to do with acceleration. So you can kind of compare the electric field strength to gravity and the acceleration constant because of comparing the formulas. Well, anyway, that was just a good side note for you. But electric field strength, just to show you some pictures of some real life things. These are just for fun, but notice this fella. And he's holding like fluorescent light bulbs. There is so much energy in that near the power lines that it is lighting up the bulbs without being connected. Now this one is actually kind of sad. This particular picture was taken by a sister. Those are the two brothers. It was right before a thunderstorm. They noticed hair standing on end, and so they were super excited. They took the picture. The only thing is there was so much electricity in the air, they didn't realize that's where lightning was fixing to strike. So lightning soon after struck, and I believe, they were all killed by the lightning. So just a visual way that you can see electric field strength, or as far as that it doesn't have to be connected to anything. Well, anyway, moving on. You have electric potential energy. Now, since it's energy, guess what it's measured in? Yep, you got it. Joules. Now, electric potential energy is how much work it needs to move a charge a particular place. It has to do with where it is, the location in the field. But then there's something similar, electric potential, which is the amount of work needed. So it starts off the same, but it has per unit charge. In other words, it's how much energy is there, how much work is needed per charge. Well, think about a couple of chapters back when we talked about specific heat versus heat capacity. Heat capacity was the whole thing. Specific heat was the amount in only 1 gram of the substance. So that's kind of the way these relate. But electric potential per unit charge. So electric potential is energy, which is measured in joules, but Q is the variable that represents it. U. Sorry about that. So electric potential, the formula for it, notice how it's energy per charge. So U over Q. And then let's say, because this is going to come into play, if you wanted potential difference. Potential difference has to do with, it actually, let me change this to potential difference, is the amount of energy per charge. And the reason why it's it is also the difference is, I'll just put that in parentheses instead. Potential difference is the change in work. Electric potential is just U over Q. And you might be like, well, what are you talking about? Well, potential difference, guess what you have to do to the two electric potentials? You can either subtract the two electric potentials, or you can do change in energy over Q. Now, potential difference, its formulas, of course, U over Q, because if they give you just one of the energies in Q, or something similar to electric field strength, KQ over R, so the only difference is the distance isn't squared. So those are for electric potential. And I'll leave that one potential difference, and I'll put the change in. And just a little vocab word. Notice how on like this charge, you've got this area around the surface that has the same charge. It's called equipotential. In other words, along that surface, it has the same charge, and there's no work being done as it moves. As long as it's moving along that equipotential surface or a surface, there's no work done. But now if you move out to a different one or move in, work is done. Here is some more. There's a little butterbean looking one, amoeba. But you can see the equipotential surfaces there. Now, a fun fact on a cube, the lines of force get so close together, if you put enough force or a charge applied to it, it can do sparks at the corners. So that's just a fun fact. And let's see what we got here. Oh, that's what I wrote. Last but not least, let's talk about the very first battery, a Leyden jar. Now, it's kind of interesting. What happened with it is, well, here. I'm drawing it when my drawings are terrible. Here's a picture of it. Rubber lid. You can see the metal rod, attached chain. They put lead on either side of the glass jar. And what would happen is they could store the charge inside the Leyden jar. And the lead would help it to do that. The trouble was it didn't last very long. So even though it was a good start, it wasn't a long-term thing. Now, it's just the fun facts about it. A guy that did a lot of work with it is actually Ben Franklin. Ben Franklin used to charge his Leyden jars by trying to use lightning. So yeah, not a good idea there. He was trying to cook a turkey one time and shocked himself. He even would use the shock therapy to try to help paralysis victims. So Franklin, he was your go-to guy with electricity. But like I said, Leyden jar, it just couldn't keep a charge. So they came up with, you'll just have to excuse my drawings, a capacitor. Now, a capacitor is something, it's made up of three things. You've got two conducting plates, and then in between, you have a dielectric constant. Let me look to see. Yeah. And usually the dielectric constant is an insulator. So plates, conductors, dielectric constant, insulators. Now there's three things that have to do with the strength of a capacitor, the size of the plates. The bigger the plates, the stronger the charge. The closer the plates, the stronger the charge. And another thing that affects it is what the dielectric, as far as its value. Now, notice how vacuum is 1, and for all of our problems, we're going to use 1. Wax paper, 2.2, paper, glass. So you can see these insulators. Ooh, look at water. That the stronger the dielectric constant, also the stronger the capacitor is going to be able to be. And as far as the formulas for it, you've got the charge per potential difference. And they would literally, you wouldn't have to find the potential difference with the other formulas and then plug in this formula. They literally give you potential difference, or that's what they want. But the formula that you probably will use the most is epsilon, which is the dielectric constant. A is area of the plates over 4 pi kd. Now, K is the same thing we've been using, 8.99 times 10 ninth. D, of course, is the distance between the plates. So you know when to use this formula. It's very obvious. They give you the distance between the plates, the area of the plates, and so it's the math is part is not that. It's just knowing units and things. And I don't know if I told you. I don't know that I did. Potential difference. Let me go back just for a second. Potential difference, since it is energy over charge or a joule over coulomb, that is a volt. So potential difference and electric potential, all of those are measured in volts. Now capacitance, since it is charge or coulomb over volt, that is 1 farad or 1 Faraday. Remember, named after Michael with the whole electric lines of force. That is 1 farad. So capacitance is measured in farads. Now you could have all different kinds of, let me see if I can find a couple of interesting pictures in your book. Yeah, there's some different kind of capacitors. You could have ceramic in there, and you've seen these with a lot of computers. I thought I had, yeah. Here's some more in my university book. You can see different ones, even ones in a computer keyboard. So capacitors, you can basically find a little bit of everywhere, especially for you people who love working with electricity, or you're going to head that way. Well, that is it. The last official chapter we are going to get to. I hope it was of help to you, and see you next week with the math ones.